Yeah. Okay, thank you very much. So, very happy to be back to ICTS after a few years. So essentially today I will do something, some introduction to the study of partition. And then it will be much more developed by Professor Surya Ramana. Then on the next two sections will be for Waring's problem and classical circle method also. And then something which is a bit different on the last talk, which is the straight line method, and not the circle method. Circle, it is the circle because the dual of the integers is r over z. But if you have a Diophantine problem, which is just on the line of the real line, then the dual will be the real line, but you may use tools which are very similar. So, okay, do not hesitate to interrupt me if there is anything wrong or whatever it is. So I will say something about use of generating function. There are two options. One option is to use a long part of the board and to write with larger characters, or to use a smaller, which is time smaller and smaller characters. If this is fine with you, I prefer to use the board and do something like that. Okay, so essentially this will be what we are going to do today. So first, I would like to do something which is not connected with the circle method, but which is a multiplicative function. Multiplicative, not function, multiplicative context. It is the proof of Euler that there are infinitely many prime numbers. And it starts with some, so the point is the following. One, you have a sequence. This is the sequence of numbers. And you have an arithmetic property, and the basic arithmetic property for primes, you are interested in primes and prime power, is that an integer has a unique decomposition as a product of prime powers. And so Euler showed the following, that for real number s larger than 1, for the time being s is equal to sigma, if you wish to use Riemann version, for all s greater than 1, when you write the sum of 1 over n to the s, and integer. By the way, when I say integer, it may depend on the context, that it is the n in the American sense or AMS sense, or if it is the n in the Goldbach sense, that is to say there may be 0 or not, just depend on the context. In some cases, it is fine to use also 0, but okay. So 1 over n to the s, you can write it as a product of all the primes of 1 plus 1 over p to the s plus 1 over p to the 2s plus blah, blah, blah. So question, to prove it, in some way you can use, first of all, you truncate everywhere. You truncate the prime and you truncate the number of prime and you truncate the summation, and you use the little exercise which is there, just for finite product and finite sums. And this you can prove by induction, definitely. And use the fact, which is great, that xy to the s is equal to xs times ys. So this is the nice property, which means that here, when you make the product, what you will get is just 1 over the product of the element. The convergence for P and for going here to infinity is not a real problem because all the terms are positive and everything has an upper bound, which is 1 over n to the s, the sum of 1 over n to the s, which is convergent. So the analysis is not difficult to go to the limit. Now you may write this as being also the product of a prime of 1 minus 1 over p to the s to minus 1. It's more compact. And now what Euler could have done is the following, to say you look at s is equal to 2. Then Euler knew a mathematician, a Swiss, from Switzerland, a Swiss mathematician, Lambert, who proved in 1760 or about, dates are different, but in any case, Euler was living when Lambert proved that essentially pi square is irrational. This is indeed the proof of the proof of Lambert. And of course, if you know that pi square is irrational, then you know that pi is irrational, which is more interesting result in some way. But so pi square is irrational. And what Euler knew, that if you take s is equal to 2 here, the value here is pi square over 6. This was known to Euler. So by those two things, he said, this is irrational for s is equal to 2. And if you have only, for s is equal to 2, everything here, every element is rational. So the product cannot be finite. So this is a proof that Euler could have done of the irrationality, of the infinity of prime. But it's not very interesting. We can do much better. It's because it doesn't give you anything about the number of primes up to a certain limit. If you take Euclid's proof tell you up to x, you have at least log x prime numbers. Is great, but here you have something much better. So you have this function, and now you do analysis. You say what is interesting, of course, is when it will start to diverge. So let us go to s is equal to 1. Of course, Riemann later on used much more than that, but it was, the start was really due to Euler. This diverges when s tends to infinity, when s tends to 1. This tends to infinity, so the number here should be infinite. Okay? So, because each term, when s is tending to 1, there is no problem about this. It's a very, very good rational number. There is no problem about that. But it gives you more, in which Euler has noticed that when this means also that the sum of the inverse of the prime is divergent. And this tells you that you are really many primes, okay? Because, for example, you have more prime than square numbers, which is not at all what Euclid was saying. And of course, starting with that, you may understand you are on the way to the prime number theorem. This is not what I want to say now. So this is multiplicative in some way because we are using this property. Okay, we are now more entering into the theme, which is the additive version. So if you take A and B, the element of A and B being the UN in your notation, let A and B be two increasing sequences of integers. For additive question, it may be interesting to keep the 0. So for an integer, n, we denote by RAB of n the number of ways to represent n as the sum of one element in A and one element in B. Okay, this is definitely the additive basic question. You take two sequences and you take the sum of the element and you want to know, for example, who you represent, how many times you represent someone. If you want to know simply whether it is possible to represent, for example, you see, when I put two, you can understand that you take more than two terms, and you can say, is it possible to represent, well, with two, is it possible to represent an integer, even integer as a sum of two primes? Then this is the way to say this number of representation has to be positive, but in some cases, and we'll see that the number of representation is interesting in itself, and even it is through this number, if you can write this number, for example, as a main term plus an error term, which is small enough, then you know that you can represent the number. There's one way to do that. Okay. So now, if you take Z less than 1, then the series, as to say in the unit disk, the series sigma A belongs to A of Z to the A, and sigma B belongs to B of Z to the B are convergent, converge absolutely. And indeed, they have nice property. They are holomorphic inside the unit disk. As soon as they are increasing, you don't want to repeat too many times the same term. But they converge absolutely. And when you write the product, sigma times sigma B in B of Z to the B, then what you get is this is the sum of R A B of N Z to the N. And here the key point, let us say 0, for example. Here the key point is that you see the parallel to this nice relation here for multiplication, the additive point that ZA times ZB is Z times A plus B. This is why the power series are interesting in additive problems. Okay? So tomorrow and in the third lecture, we'll consider a case when the sequences are powers, the set of powers of element, that is to say, Waring's problem. Okay? For today, we'll look more at essentially partition function, because in some way the circle method was first introduced by Hardy and Ramanujan for the partition function, and then Hardy and Littlewood noticed that it was possible to extend it and to work on the Waring's problem with the same analysis, same sort of analysis. Okay. Yep. Sorry?
Ramanujan and Hardy have started studying
Yes.
kind of...
Yes, they also did some. Yeah. Right. Okay. So fine. So this is the generating function, and I am going slowly towards partition function and start with the limited partitions. I don't know if this is the official term for that. I will tell you what I mean by that. Let M an integer, be an integer, okay? And we assume that we dispose of unlimited, whatever you like, unlimited number of coins. It is also phrased with the postal stamps. With the nomination one, two, blah, 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 M. course, you can do also something when you consider the real value you have. That is to say, you have coins or banknotes of $1, $2. It exists, but it's never used. $5, 10, 20, 50, and in how many ways can you do something like that with interesting other problems? If they are not all equal, when do you start if there's no one in it? When do you start to represent everybody? Okay, but so we dispose of unlimited number of denomination, and we want to know what is Pm of n, then denotes the number of ways to use the coins or getting the amount n. Okay? So for example, if you look at the number 5, let us say m is equal to 2, just example. M is equal to 2, and so you have just denomination 1 and 2, and you want to know in how many ways you can represent 5. That is to say, what I would like to write is the following: what is this value? The exercise, I want to do this. So you try to see what you can do. Of course, you can do 5 times 1. You can do 3 times 1 plus 1, 2. You can do 1 plus 2 plus 2, and that's it. So this is, that's it. That is to say that we consider the ways which are essentially distinct. We are not counting, for example, exchanging here the value of 2 and taking 2, 1, 1, 1. This will be the same. You can always write them, for example, in non-decreasing order. And then this is essentially different from this one because it's not by reorganizing that you get from this to this, but you don't count the one when you exchange the thing. So we'll see how it is. So this is 3. Fine. Okay. So now the point is to try to understand what is the generating function of this. We know that for additive question, we have an additive question. What will be interesting is to have something which is the generating function of interest for us will be the summation over n of Pm of n times z to the n. This is the generating function of interest. Okay? And so we want to express it in a better way, in another way, and try to do something like that. So if you understand what we mean, we can write it in a slightly different way. This is the number. You see, I can here say, this is one way to write it. Another way to write it is to say, how many times do I use a coin of 1? How many times do I use a coin of 2? How many times blah, blah, blah. So this will be 5 times 1. This will be 3 times 1 and 2 times and once 2. This will be the way to get 5. This will be 1 times 1 plus 2 times 2. This is 3 times 1 and a 2, and this is, each time the sum should be equal to 5. And if you say, I have at my disposal 1 and 2, and what about 2? You can write here plus 2 times, plus 0 times 2. Okay? And then you may say, what is P2 of 0? P2 of 0 as a representation, this is the empty representation. This empty representation corresponds indeed to 0 times 1 plus 0 times 2. And it will be better in this context to consider that this is definitely n non-negative integers. Because your power series will start with a 1. This is one representation, and this is the unique representation. So it's better to see it like that. This is the number of h1 blah, 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 hm. You understand that this can be done if you are not taking all the values up to m. And if you are just taking a subset of the coins, you will have exactly the same type of representation. So this will be, in my representation, I am saying this is the number of 1 and the number of 0. This is the number of 3 and the number of 1. This is the number of 1 and the number of 2. So this is h1, h2. Here it will be 5, 0, if it will be 3, 1, if it be 1, 2. So we are looking at those h. What we say that hi are all non-negative. We don't care about the number, but it has to be taken into account in here. Okay, hi is positive, and what is important is that you have h times 1 plus h2 times 2 plus blah 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 plus hm times m is equal to n. Okay? So now this gives us the clue to know how to write this power series, always using this wonderful thing that each time you have a sum like that. So you have a sum of terms of this type. So somewhere you should find z to the h1, 1, z to the h2, 2, and so on. So what you write is that you defined, you let, okay, 1 plus, maybe I write it with x because I'm essentially using real numbers now. So x plus x2, consider. It's not let, it's consider. Plus blah, blah, blah. So infinite product, but it converges pretty well. So you may write x is less than 1. You may consider that it is a complex number if you wish, but we are essentially going to look at real values. Oh, no, we are going to consider complex values. Also, no problem. Okay. 1 plus x2 plus x4, all the even numbers, multiple of 2, plus blah, 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 up to 1 plus xm plus x2m plus blah, blah, blah. Now, if you look at this product, what you can get is exactly the number of representation you have for n. This is indeed the sum when n is positive of pmn xn. Okay, always by the little exercise which we didn't do at the beginning. Okay, so you can also write it as we did for the sum of powers. We know how to sum the powers, geometric progression. And so this will be 1 divided by 1 minus x, blah, 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 1 minus xn. Good. So now the problem is fine, but it's to know what can we do with this in order to get some information about Pm of n. Okay? We are in a good case. In some way, we are not with the infinite series. I leave the infinite series to Surya. But this is a finite. So essentially, this is a rational fraction. It is just a fraction. So you have something which I think in English it's called the partial fraction decomposition of it. So look at the fractional partial decomposition. Fractional, what do you say? Fraction. No. Partial fraction. Decomposition of this rational fraction. Yeah, it turns out that large part of the English vocabulary in mathematics is from Latin or Greek, and so we are using essentially the same, but we have some other way to write that, and décomposition en éléments simples. So, then it means the following, that, okay, you have 1 minus x, but 1 minus x occurs here, occurs in any place, because this will be 1 minus x times 1 plus x2 plus blah, 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 plus x m minus 1. Or you just notice that all the roots occurring here will be roots of unity. So the 1 will occur with a higher power, it is 1 minus x, because it occurs everywhere here. So this will be something like a, I don't put indexes, there's no point to do something like that, 1 minus x to the m. And then you will have something, or of course then plus maybe a, let us say am, I don't know, am minus 1 over 1 minus x to the m minus 1 plus blah, blah, blah. And then you'll have, what will be the next? The next that will occur at least half of the time is the root minus 1. That is to say, you will have 1 plus x, and 1 plus x, you have it essentially m over 2 times, integral part of m over 2 times. And then you will have the b, m over 2. Let me write m over 2, don't care about that. 1 plus x to m over 2. But all the exponent, then you will have, for any root of unity which occurs in this product, if it is not 1, it will be at most m over 2, the number of times it occurs. Okay? This is interesting, because now if you expand this, how to get the expansion? So you can now take the expansion of each of these guys, sum them, and you get this expansion. But how do you get the expansion of 1 minus 1 over x squared to start with? You know how you do that. This is not really analysis, but although it looks like, it is just the different, you take 1 over 1 minus x and you differentiate it. And when you differentiate it, you just get downstairs the 1 minus x squared, or you write it as you wish. And above there will be a minus 1, but there is also a minus 1 here, and everything is fine, is what I wrote here, hopefully. Okay. This is interesting because you know the expansion of this one. The expansion of this one is exactly this expansion. So when you are going to look at the differentiate, what you get is that 1 disappears, x becomes 1, x2 becomes 2x plus 3x2 plus blah, 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 plus essentially n xn minus 1, or n plus 1 xn, as you like. So it is something of degree 1. And since here you are differentiating m times, this is the way you will get this one, what you will get is each time a polynomial of degree m minus 1. So here you have something which is an expansion with coefficients which are polynomial of degree m minus 1 in n. Okay? Here it will be of less degree. This will be of less degree. This will be of less degree. So essentially, it tells you immediately that Pm of n is a polynomial of degree m minus 1 in n. So this is not circle method, but it is the use of generating functions. Everything is good to use in some way. Fine. And even if you want to know what is the first term, you know what is the first term, you know how you get the AM. Well, I think this is rather classical, but you multiply everything by 1 minus x to the m, and so then you get something here that you can evaluate. Of course, it will give am. All the other terms will disappear, and this am will be what you have. Let me say this is fine. This is enough. Yeah, I multiply by 1 minus x to the m, and I can evaluate this function. And I let x tend to 1. Yeah, I let x tend to 1, so all this disappears, and then for x is equal to 1, once you have suppressed all the 1 minus x below, you can take the value at x is equal to 1, there is no problem. Okay, fine. So you can even say, what is this dominating term? And you can say a few things. So you have some good knowledge of this. Okay, maybe we go to the partition function. I'm wondering whether instead of saying 45 minutes, it's maybe better to stop here for 5 minutes and then we'll devote 1 hour to partition function. If you have any question, of course, you are welcome. I can erase everything here. It's okay. I don't think I need that any longer. The board is very good.
Yes, sir.
And the chalk is also good. I mean, both are really working well. Okay, I let you this. Thank you. Hein? Ah, très bien. Le tableau est parfait. L'accord entre le tableau et la craie. Oui. Can parler comme ça? Oui. Mm. Nous avons une collègue à Bordeaux qui parle comme ça. Pierrette Cassou. Oui. Bon. Yep. Okay, so we live now in a country where there are infinitely many coins of any denomination. Wait a minute. If I lose too many pages, I am in bad condition. Yeah, this is fine. Oh, I don't know which is the number, maybe 3, the partition function. Okay. So there will be, of course, some overlap with what has been said this morning by Kannan and Ramanujan, but I don't think it's too bad that we have some repetition. There may be a slightly different point of view, and okay. So now the partition function. P associates an integer n the number of, let us say, essentially distinct ways to represent it as a sum of positive integer. It is little p, p of n. So this is the partition function. What is p of 0? How many times can you represent 0 as a sum of positive integers? There are 2 answers. The natural one is to say, no, it's not possible. But another one is to say, yes, there is one representation, which is the empty representation, with 0 of each of them. And as we have seen with PM of n, it's much better. The second way is much better. So P0 is 1. Let us take it. This is a convention, but then all the expansion in series will work if you put P of 0 is equal to 1, otherwise you have problems. Okay, so because now you know what it is, because P of n is just let me just recall it quickly. This is the number of H1, H2 of the sequences, blah, blah, blah. Then there are infinite sequences such that H1 times 1 plus blah, 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 plus Hk times k plus blah, blah, blah is equal to n. And indeed, if n is equal to 0, you have one possibility, which is 0, 0, 0, 0. And if you don't put 0, then you are in trouble if you don't accept 0. So it's fine. And again, you have the generating function, f of x, which is the sum over n positive 0 of p of n xn. Additive problem, and so this is fine. It gives you the same product, except that now the product will be infinite, and so it will be the product when m is equal to 1 to infinity of 1, what am I doing here? Yeah, 1 plus xm plus x2m plus blah, blah, blah. Okay. And this converges on the unit disk uniformly. Well, okay, just little analysis, and I don't want to go into that, but okay. So, and convergence now, so you have a nice function, f is holomorphic in the unit disk. Okay. Fine. So first consequence is that P of n cannot be too large. It cannot be too large in the way that log of Pn, by the way, today I'm essentially going to work on log of Pn, and Surya will tell you more than that. Log of Pn cannot be larger than constant times n. Because if it is exponential type, then the radius of convergence will be smaller than 1. So already from the fact that this converges, you have some information about P of n. P of n cannot be too large. It cannot be exponential. Now there is also something which is rather clear from the definition, that for any m, P of n is larger than Pm of n. Number of representation by all the denomination is larger than the representation with only pure restricted denomination. But we know that this is a polynomial of degree m minus 1. So Pn is tending to infinity quicker than any polynomial. Yeah? So f, you know what it is? It is in some way sub-exponential, but quicker than a polynomial. Well, you have a large margin in between. So we try to understand a bit better what can we say. We can say something about log of Pn or about Pn or something of the kind. Okay, this is done. This is not. There's nothing to do here. Yep. Okay. Well, so now if you want to know something better, you need to have some more information about f of x. Yeah? So to get some information about f of x, well, this is fairly explicit, so we should be able to give something. Now, the product may be a problem. If you don't like product, you take the logarithm. Exactly like for prime. This is the difficulty with zeta. Zeta is a very nice function. It has only one pole, and we know the residue, where it is, we know everything, and beside that, it is very good. But to study the prime goes with the product of prime. So if you want to do something, you have to take the logarithm And then here's the mess, that the singularities now for log of zeta will be the zero of zeta. And this is why you are interested in the zero of zeta. So here the situation is better, but we take the log of this business. Oh, by the way, there is also one way to write that. No, let me stop here. Okay, let us study a bit what is log of x. So to get more information, I want to go to something like that. This will be easier. This is the sum when n is equal to 1 to infinity. Maybe I should keep the notation m. I hope I will not do something stupid with that, but log of 1 over 1 minus x to the m. Okay, and this is the summation that was given by, now I start to be confused. This is the sum, let us say, from m is equal to 1 to infinity, and then it will be the sum from n is equal to 1 to infinity. I developed the log in 2 powers nm divided by m. This x is smaller than 1, so I can develop that. Okay? And if I regroup the term, slightly different from what maybe k is equal to 1 to infinity of xk divided by k 1 minus xk. Okay, it's somewhat different from what what Canan was writing, but all that is correct. So we have tried to see what it can be. 1 plus x plus x n plus xm. God, I keep what is written here. This is less than m because we have m terms which are, some are less than 1. So you have this. This is for x real. When I write something like that, it means, of course, that I am just taking real values. But on the other hand, it is larger than what you get if you take the smaller one, which is xm minus 1. And from this, you should be able to deduce, it is little computation. I don't like to make computation on the board, but okay, maybe I give you this and then you'll think of it. 1 minus x summation m is 1 to infinity of xm over m square log x, log f of x, and this will be less than 1 over 1 minus x summation m is 1 to infinity of x over m square. Okay, this is just using this thing. And this is fine because it tells you what is log x. You see that there will be a singularity at x is equal to 1. Of course, this was already the case for PM. And for PM, even the singularity was more important for 1 than for 1/2 of 4. There were other singularities, but they were less important. This will be important, and maybe if you think that what you have seen from PM minus 1 can be transferred to PM, when we are going to study PM, we'll see different singularities, and there will be some situation. It is quite possible that what we see is that the singularity at 1 gives 2 terms which are more important than the singularity for 2. You remember in PM, singularity for 1 was giving you something which was a polynomial of degree m, and for 2 it was giving you a polynomial of degree m over 2, that is to say the square root. So there you will have different singularities. We don't contribute in the same amount. This will be an opposite situation for the Waring's problem. We'll see different singularities, and they will contribute with the same order of magnitude. which is not that nice, by the way, but okay. So we see this singularity. This is for the time being the first one we are concentrating on. And then, of course, when x is close to 1, you see that this will be sum of 1 over m squared. This will be, again, the sum of a 1 over m squared. That is to say, our favorite pi squared over 6. So we have the following, that when x tends to 1, log of f of x is equivalent, x tends to 1, being smaller than 1, of course, that pi squared over 6, 1 minus x. Okay? And this gives you already information about, always go to see what is the behavior around the singularity, and you'll get something back. Exactly for the prime numbers, this is what we were doing, and this is what we are doing here too. Okay? So there is a little exercise that you can do. Exercise, I don't want to make it here, but exercise. Assume that P of n, if you don't like to write it P, let us assume something like P tilde of n is, you see, we are looking for a function which is in between exponential and polynomial. So we are expecting something that it is exponential of something which is smaller than linear, exponential of square root. Okay? And assume that you have this, and that the generating function, f tilde of x, is equivalent to pi squared over 6, 1 minus x. So here I give something that I know already that this is very well defined, okay? So if I have this, then show that this to say where it comes from, the two coefficients, you see, a and b for that. Show that b is equal to 1/2. This is the easiest one to get, and a little bit more computation, but there's nothing too difficult. 2 over 3. You may multiply above and below by 2, and if you prefer to write it as 2 pi over square root of 6, it's fine, you are welcome. Multiply by square root of 2, numerator and denominator. Okay, so this is little exercise, and what you have to do is the following. This, you call that, yeah, I'm here. This I called alpha n. No, it's better to give you the hint, because there is always this saddle point method to know where you have to go and fetch information. So it's important that I tell you. Okay, so let x, we have to determine it before, in 0, 1, to be determined. We determined. This will be the x which is here and the x which is here. Okay? And we defined y is equal to minus log x. Or if you prefer, x is equal to e to minus y. This will be the good thing. You see, it is a real number between 0 and 1. So it's good to say that it is exponential of something negative. So y will be positive. Okay. So f of x, or this x, will be the summation over n of e to the a n to the b. This is just what you have for the p tilde of n, f tilde. And you have now x to the n. X to the n is e to the ny. Okay? So, sorry? Yeah, minus ny? Yeah. Xn? Yeah. I write p tilde of n, xn, because this is the generating function. I didn't write what it was, but it is just, yeah. xy of n, call that alpha n. Okay? So now when you look at this in n, this function is decreasing. And it's decreasing exponentially quickly because it has a minus n. It is linear here, okay? Or x given. Okay? So now you choose, you select y such that alpha n of y is maximal at n is equal to capital N. Okay? So I will select one value and say that for this value will be already almost everything, is the point. Okay? Okay, that is to say that you want y is such that a, b, capital N to the b minus 1 minus y is 0. You just differentiate this in n. Okay? And you say that you want the derivative to be 0 at little n is equal to capital N. Derivative is n is just a, b, n to the b minus 1 minus y. And you say I want it to be maximal, this quantity to be maximal when little n is equal to capital N. And so you choose the derivative to be 0. Okay. So now there are some computation which are not very funny, and I don't want to do all that. But what you will get is something which will be, okay, we shall get it's just a few lines, but there is no point to write that. What is important is to have f of x will be exponential. I don't want to write the constant. The constant is important to put in of 1 times c tilde times 1. What is important is to have this 1 minus x to the b divided by b minus 1. In this c, you will have a few things, including the pi, including different things, including b itself, and so it's a mess. But what is interesting is that here, from this, we know immediately what should be the b and why it has this shape. In some way, we are explaining that the fact that the log of f, whoops, the log of f tilde is this. Ah, no, I defined, yeah, okay, I see what I do. I should write, yeah, I should write G, because the log is already incorporated in that. Okay, so the fact that you have here 1 minus x is indeed why here you need to have b is equal to 1/2. Okay? So in some way, you have some sort of, should be Tauberian theorem, which tell you that if you have this behavior for log of f, then the behavior is something which is exponential of a square root. This is the only point I wanted to mention here. So then, b is equal to 1/2. 1/2 divided by minus 1/2. So it is minus 1. It's exactly what you had. And now, if you follow blah, 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 the value of c tilde, then the value of c tilde will tell you what is the value of a. Okay? And this, if you make the computation, through the exercise, this implies that A has the value you wish. A is equal to 2 pi over square root of 6. Okay. So now with this, we can work a bit on P of n itself and show that indeed log of P of n, and show that log of P of n has the expected value. So now we claim, I will give you some idea. Log of P of n is less than p square root over 3 plus little over 1 and 1/2. We can indeed prove that it is at most this, always from that. This was just in some way an exercise where we were assuming that a priori it had this shape, and to say if it is exactly equal to that, then the value will be, since it is some exercise like that, there is no point to say, assume that it is equivalent to, or that it is almost, there is no point to say if you assume that. So it gives you some idea. So we are not going to use, of course, anything in the exercise. Exercise will just for us to give some philosophy behind. And we use, you maybe heard this morning the name of Rankin. And the Rankin was doing that in several instances, that to get an upper value of something, take some generating function and evaluate it at the right point, essentially when the term you are interested in, the single term, will be dominating. You choose the parameter. So you introduce one parameter, you get a function, you know something about this function, and you choose the point where for this parameter it is optimal. And this is, by the way, exactly what we were doing here, the choice of the optimality. Okay, so you have to know where you look at that. And so the proof is easy. You have to choose the right point. Let x be exponential of minus pi square root of 1 over 6 times n to the 1 minus 1/2. You do it in some way by brute force, but brute force is helped in some way by what we have been doing. And if you compute it at that, then the only thing you have to say is that Pn xn is less than f of x. Yeah. Less than f of x. Yeah, this was something that the logarithm there. Okay. Less than f of x. And then you compute it for this value. And when you compute it for this value, you find that this is exponential of 1 plus little o of 1 pi square over 6, 1 minus x. This is what we know. This is when we look at the maximum. Okay. And you know what is x. You know where you have an upper bound for Pn xn. So you have an upper bound for Pn. And for you take the log of that, and when you take the log, you get this. Okay. So end of the proof. Okay, now we can do indeed even better. That you have also a lower bound. It's a bit more complicated to get the lower bound, because you see for the upper bound, you have the series, you know everything about the series, you know well what it is, and you just take one term. You expect to take it You do everything so that the term you are going to choose as the maximal value. But what about the other terms? So either you know that something is smoothly decreasing or well decreasing so that the contribution of the other one will not be too large, then you are happy. Or you have an upper bound and then you try to find something else. And what I will suggest you, just some little exercise. So let us write first the proposition as n tends to infinity. Tends to infinity, we have log of Pn is equivalent to what you like, P of 2 square n 1/2. Okay? So the upper bound is fine. Indeed, it's possible even to prove a bit more. You don't need to put a little of 1 here. This is a real upper bound. And for the lower bound, what we use, or one way to do this, is to use some recurrence relation. So for the lower bound, use the recurrence relation NPN. So this has nothing to do with the circle method. And H times the summation when K is between 1 and N over H of E of N minus HK. There are several relations like that. So it is combinatorics, this, the proof you have to count things. So the number of partitions of N having at least K times the integer H is this, is Pn minus HK. Because you say that you force it to have at least H times the number K, and the rest is just any partition will do the job. Okay? So this is what you are doing. Thus, the number of them with exactly 1 time the integer H is Pn minus H minus P2H. Okay. The number of partition. So this is a proof of the relation. The number of them with exactly 1 time is exactly 1 time H, the summand H. So it is P of H minus N minus H. That is to say all the ones which have H, but if they have at least 2 times, you don't count them. So this is minus P of N minus 2H. Okay, fine. And the contribution of H, all partitions of N is H time the contribution. This is the number of times, but I am counting the contribution of H. And so it is H time, the number of times it occurs. So it is H, Pn minus H minus Pn minus 2H plus 2H blah, blah, blah. Okay, when you have 2H, this will be P of N minus 2H plus minus P of N minus 3H and so on. Okay? And this is exactly what you get here. And this is just the contribution of all the H. And this is exactly what you have when you have n times Q of n. Good. So this is fine. And essentially, this permits you to get some okay, let me write what I want to do. I am not going to do the job, but proof by induction exercise. I mean, what is just a first year of university with some, even if you need some details, it's just boring to give here. Proof by induction that for every positive or any epsilon positive, there exists AH positive such that Q of n is larger than 1 over A epsilon exponential of P square root of blah, 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 as usual, 3, minus epsilon n to 1/2. When you know what you have to use, it's okay. So this is statement of the exercise. So maybe I say a word on eta function. It's fine with you? You are going to go into it, or you use it? Maybe I say a few words, or no, but it's not the point. But okay. So we are back to the generating function. So a word, let me say a word, maybe cat 4, 5, I don't know. A word on the eta function. So what you have is this, that f of x, the generating function, is 1 over 1 minus x, blah, 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 1 minus xn, blah, blah, blah. Okay, this is the, the eta function you have. Now, the situation is the following. You have seen it this morning. You will see it again, that the way when you have this, and of course you write it also as summation. So this is fine inside the unit disk always. And this is the summation of P of n xn. So the way to recover Pn is just to use Cauchy formula. That is to say, you divide by xn plus 1. So you create a pole just at x for 0. And so now, if you can compute the value of that just by the residue of it. And so you just have also, you can integrate over around 0. Wherever you are, it has no importance, of course. So then what you will do is to go to a circle which is close to 1. As usual, you know, this is where you are going to get something by the interesting by the you call that steepest descent or the saddle point method. Yeah. Okay, so you are going to integrate that, and the point is that if you are far away from the pole, what you will get is usually something which will be some sort of error term. And the situation will be around the pole. So around the pole, the problem is that you have to know something about the function. And with this function, there is something very nice, is that you can essentially write it as a product of a term which is well controlled, which will be the same function, but at the, rather far from the pole, and a nice function. Okay? So this is the modular property of this. And it is why for this function, it's very important, not even if you are interested in Pn, you can say, oh, I can use only the summands which are less than n and truncate and have finite sum. But this will be a problem because you cannot use this. Okay. So now you know the Ramanujan function, and you will recognize this. The tau function, okay, and 0 to infinity of tau of n, is it n 0? Yeah, well, for 0, if you put t of 0 is equal to 0, if you don't like, you put this. Because it is that times the product of 1 minus Zm to power 24. And this function has nice property. So this is fine, except that you have to take the 1 over 24th power. And for a complex number, you prefer to know exactly which determination you are going to use. So it's not the best thing to stay with Z. It's maybe better to expand it with the radius and the argument. Okay? So indeed, what you look at the following. You take H, which is the set of tau in C, for which you will see why imaginary of C has to be positive, is fine. And then you have a way to send this into C by the following. If you have a U, you associate to U exponential of 2 pi I U, your favorite exponential of 2 pi I. Of U, and the image of H well, if you take U, which has imaginary part which is positive, it means that the real part you'll get from here will be negative here. And so it means that the radius is less than 1. And so you are exactly in the unit disk. So this is the advantage. This is a unit disk. Okay? Sorry? The unit disk minus 0. Yeah. You are right. You're in some way to put one point at infinity if you want to recover 0. Or just when you turn to 0. Okay, fine. Okay, so then it is better to use it that way. And so to consider indeed the function, which is delta of U, which will be the same as this one, but delta of U is E of U E of u is this, z, times the product when m larger than 1 of 1 minus m minus e of mu to the power 24. Okay? And imaginary v is positive. Okay. Fine. Now, when you have this makes some sense to take the 24th power and to introduce something which will well done, which will be the Dedekind eta function which is eta of u. Of course, taking the 24th power of this is not complicated. The right candidate is this one, but this is for this that you may be in trouble. But then this is fine because you simply take the natural 24th root of u and the product m larger than 1 minus e of mu. And this is the function which has, so you see that this is very close to what we need here. We always need this problem, but the nice thing to do will be this. So this will introduce in some way, this function is in some way invariant by some transform. I'll say a bit more about that. And everything would be almost too perfect if everyone had this. But this is a nice function. And this will not give something too complicated to get, and it will give you even a nice term. Okay? So just I tell you what is the transform of the eta function. Yeah, I think it's fine. I have time to do that. So let gamma, which is ABCD in SL2 of Z. SL2 of Z means that the determinant of gamma is equal to 1. So it is invertible in Z. Okay? And gamma acts indeed on H by gamma u, which is AU plus B divided by CU plus D. And you can really verify that if U is in H, then gamma U is also in H. It's fine. Okay? And really what is important is this. We have the modular relation eta of gamma U is essentially Cu plus D to 1/2 eta of U. So eta of gamma U is eta of U. Plus something, this is a nice term. We have another term which is not too complicated with the theta of gamma, which is just a root of unity. And I can give you what will be important if you are interested in the main term. What is going on when you are around 1 is that one of the gamma is 0, -1, 1, 0. Determinant is equal to 1. The integer coefficient determinant is equal to 1. And if you look what is this is by definition 0 times u minus 1 divided by 1 times u. And this is just the inverse of u. -1 because you want everything to stay in H. Okay? So this is the inverse. Okay. It's fine because you see, if you are in a line, if you integrate in a line which is close to the border of the circus, it will mean, the circle, it will mean that you are on a line which is rather close to the real part is equal to 0. And if you take some inverse, so if you have close to 0, then if you take the inverse, boop, you are in a good place. You go almost to infinity, it's nothing. You have good knowledge. You are very far away from the infinity. So instead of summing this function when you are close to the difficult point, then you can replace it by something. Of course, there will be these terms to take care, but those terms are nice, so you should be able to integrate them. You'll talk about four circles and everything to do that. And if I could give you the value of theta, it's not very funny to write what is exactly theta. It's well explicit, but for us it will be I to minus 1/2. Yeah, okay. So in some way you have something which is f of ux for the function. If this is needed to you, I don't know, f of e of ux, this will be u over I 2.5 times e of 1 over 24. By the way, in h, you know what is the square root? Because you have always two points, and one is in h. So the square root is well defined in h. E of u plus 1 over u times f of e of minus 1 over u. This will be the thing which will be. So possibly, and then no, this would be asymptotic equivalent. I better not touch more of the topic. So we stop here. At your disposal for questions or. Okay, thank you.